Hello everyone, today we'll be talking about nautical time and the different types of time that we use as navigators and assistant navigators to get where we need to go on time. And also we'll use it as an introduction to some celestial definitions. This first part, we'll go over most of those definitions and we'll introduce you to the nautical time concepts that we can build on later in the course. For references, we'll be using Bowditch, Pub 9, as well as the nav dorm. And we'll also talk briefly about NWP 1TAC 03.1. That's where we get all of our operational reports from, such as move reps and CAS reps. For us, we're mainly concerned about those move reps because they give us PIM, position of intended movement, and we'll have to calculate that later in the lesson. And last, we'll be using our nautical almanac. We currently have the 2018 version. On your ships, you'll have the current year, but we'll show you how to use it so that you can calculate everything from sunrise, sunset to where a certain star is at a certain point in time. At the end of this lecture, if we give you applicable charts and emission, you'll be able to explain how time and timekeeping is required to establish a ship's position, your ship's position, on the Earth in all types and all phases of navigation. And we use those skills to develop a safe voyage plan in accordance with Bowditch. We'll accomplish that terminal objective by our enabling objectives. If we give you a location in time, a location in zone time, you'll be able to convert it from zone time into GMT, Greenwich Mean Time, in accordance with Bowditch. You'll also be able to do the opposite. So if we give you a location in GMT, you'll be able to convert that from GMT into zone time, in accordance with Bowditch. Also, if you give you a location in local mean time, LMT, you can convert LMT to zone time in accordance with Bowditch. And if we give you a voyage plan, you'll be able to determine the zone time of arrival at the destination in accordance with Bowditch. Those will be our ETA problems. If we give you a voyage plan, you'll be able to determine the speed required. Those are our speed required problems to arrive at the destination in accordance with Bowditch. And if we give you a nautical chart and plotting tools, you'll be able to determine if the ship is ahead, behind, or on PIM, position of intended movement, in accordance with Bowditch and operational reports, NWP 1TAC 03.1. Let's get started. Time is critical to the navigator, and there are lots of different types of time, so we're going to go over most of them so that whenever you have four numbers, hours and minutes, there should be something after that to tell us what type of time that is. There are lots of different types of time. For us, we have used the sun to make our calendar. So one day, 24 hours, is the time it takes for the Earth to do one full revolution. So the sun rises once and sets once. Our year is based on how long it takes us to orbit the sun, about 365.25 days. So we mainly use solar time. However, many different cultures and many religions out there use the moon, so they use lunar time. The Roman Catholic Church, Judaism, Islam, they all use the moon for their calendars. So maybe you've been in Fifth Fleet and you pulled into a port, and what do you know? It's Ramadan. That's based on the cycles of the moon. So depending on where you're going, it helps to know what type of time they're keeping. And then there's also sidereal time. That is based off of the stars. We rarely use that, and the navigator does not need to know how to use that. However, they've used that for hundreds of years, so when we get into the more advanced celestial later on, if you know sidereal time and how it works, that will certainly help you to grasp the theory. Bottom line is that all navigation is based on some form of time, so whenever you have numbers, you need something after it, whether it's ZT or LMT or GMT, to tell us what type of time that is. Our first type of time is Greenwich Mean Time, GMT. Almost all types of time will have a reference point. In this case, the first word, Greenwich. Whatever the time is at the Greenwich Meridian is GMT. The Greenwich Meridian is also called the Prime Meridian. They both describe the same thing, 000 degrees of longitude. In the military, we often refer to GMT as Zulu, because each time zone has an alphabetical designator. In this case, Greenwich is Z. So for our intents and purposes, GMT equals Zulu. If you take a look at the world, we'll see that Greenwich is at 0 degrees longitude. And the reason we call it Greenwich is because it's that line, that longitude, 000 degrees, passes directly through the town of Greenwich in England. The Royal Observatory was in Greenwich, England, and that's where all the British astronomers made all of their tables for their almanacs. Now, every country had a different prime meridian. So the US, we used Greenwich, but the French used Paris, the Russians used St. Petersburg, the Spanish used Cadiz. So in the 1880s, the world came together and said, you know what, we need to have the same reference point. So that's where we came up with Greenwich, England, in the mid-1880s as the prime meridian. Our next definition is Coordinated Universal Time, also known as UTC or UT. For our intents and purposes, UTC is equivalent to GMT because it's very rare that there will be a difference of more than a second between the two. GMT is the mean time at Greenwich, whereas UTC is based off of atomic clocks. Depends how fast the atoms of the radioactive element cesium is moving, so that's way beyond our level. If you're a physics major, that's probably interesting to you, but for us as navigators, it's the same because the difference between the two, so DUT1, will be no more than a second. Basically, the U.S. Naval Observatory will reset the atomic clock in either June or December with that leap second, and you won't even know about it. The GPS time you get will just be, they'll update it and it will be transparent to you. So whenever you see UTC, for us it's equivalent to GMT, which is equivalent to Zulu. If you look in the Nautical Almanac, they use UT, Universal Time, which again is equivalent to all of these. Our next definition is zone time. That's the one that we mainly use. Most of our watches and clocks are set to zone time, or very similar to it is called civil time. And so just like any other time, it has a reference point. Our reference point for this one is the time zone that you're in. We instituted this because it makes a lot more sense. Instead of everyone having slightly different times, anyone in the same zone, time zone, depending on your longitude, will keep the same time. So that when you travel 20 miles east, someone's not keeping a different time that's a few minutes off. It all depends on what your closest central meridian is. We'll go over that in a few slides when we talk about zone description. And whenever we say a time in zone time, we'll label it as, let's say it's 0900 ZT, zone time. Not Z, because that's Zulu, which is equivalent to GMT, but ZT, zone time. If we take a look at our time zone map, we'll see that since this is the US, we are currently right about here. So this shows us that anyone in this time zone from here to here will be keeping the same time on their watch. And then once we cross these boundaries right here going into this time zone, that's when we would change our watch time because we'd be in a different time zone. Very closely related to zone time is local mean time. The reference point is the local meridian, so the one that you are on, rather than that central meridian that we use for zone time. The only time we'll use LMT in this class is when we refer to LMT at Greenwich. The Nautical Almanac gives us a lot of different times for different celestial phenomena, so whether that's sunrise, sunset, or moonrise, moonset, or meridian transit, it'll give us that LMT at Greenwich, and then we'll be able to do the math to get from LMT into zone time. And we'll do that later on in this lesson. The good thing about LMT at Greenwich is that if something happens at Greenwich, at LMT, every central meridian will have the same LMT as the one at Greenwich. So it makes it much easier to do our calculations. And we really need to make sure we know the difference between LMT and zone time because the Nautical Almanac mainly gives us LMT. not zone time. It's up to us to figure out how to get zone time from LMT. So whenever we talk about LMT, just think about the LMT at Greenwich and every standard meridian. Next up is our zone description. This helps us when we are trying to go from zone time to GMT or GMT to zone time. It consists of ZD, and then either a plus or a minus, and then a whole number, for instance 5. And that tells you what you have to do to get from your zone time back into GMT. So let's say that this is ZD plus 5. We would have to add 5 hours to the time that we're keeping in our time zone to get to GMT. And if it's plus, that means we're in the Western Hemisphere, because we'll always have to add time to get to GMT, because Greenwich is ahead of us. If we're in the Eastern Hemisphere, it'll actually be minus, because the Eastern Hemisphere is ahead of Zulu, so we have to subtract time in order to get to GMT. To determine your zone descriptor, you take your longitude and you divide by 15 degrees, because each time zone is made up of 15 degrees of longitude. So let's say our longitude is 0.75 degrees west. We'll plug that into our calculator, divide it by 15 degrees, because there are 15 degrees in every time zone, and we get 5. So that's the number of the zone descriptor. The next thing we need to get is whether it's plus or minus, and we get that from either east or west. We're in the Western Hemisphere, so it'll always be plus. Now, that's an easy example. Let's try a slightly trickier one, because we won't always be exactly on a full degree of longitude. Let's say our longitude is 039 degrees, 14.8 minutes east. All right, following along the steps, we're going to divide that by 15 degrees. But, we can't put this number into a calculator, because our calculators can't do degrees and minutes. So instead, what we have to do is we have to convert these minutes into degrees, which means we're going to take our minutes and divide by 60, because there are 60 minutes in each degree. So we'll take 14.8 minutes divided by 60 minutes, put that into a calculator, and we get 0.247. And that's in degrees. So what we just did is we took 14.8 minutes and we converted it into degrees. So this number, 14.8, is equivalent to this number, 0.247 degrees. So now we'll get rid of the minutes. We'll replace them with the decimal degrees. And now we have a number that we can put into a calculator. So we'll take our full degrees, we'll divide it by 15 degrees, because there's 15 degrees in every time zone, and we get 2.62. Now our zone descriptors will always be whole numbers. So we will take the number we get and we'll round it to the nearest full number. In this case, 3 is closer than 2 because of our 0.62. So we're going to round that up to 3, and our zone descriptor is 3. To find the sign, we look at our longitude. We're in the Eastern Hemisphere, so it'll always be minus. So we just found our zone descriptor based off of our longitude. We're in ZD minus 3. Quick note about rounding. As you see over here, I went out to 2 decimal places. I prefer always to go to 2 decimal places just to keep it consistent. You can round as much as you want, but we want you to be accurate. When we talk about zone descriptions, the rule is if the number you get is 0.50 or higher, you will round that up. If the number you get is 0.49 and less, then you will round down. That way, we'll keep it consistent. If we take a look at a time zone chart, we'll look at Greenwich right here. So that's 0 degrees of longitude. That is ZD plus 0. The next time zone to the west, in this case to the left, will be ZD plus 1. And then as you go west, it'll increase ZD plus 2, ZD plus 3. Whereas if you're in the Eastern Hemisphere and you're heading east, those numbers will go ZD minus 1, ZD minus 2, ZD minus 3. Now on to daylight savings. Many of us are probably familiar with this because in the spring, we spring forward an hour, so that day only has 23 hours in it. 0600 zone time becomes 0700 zone time. Whereas in the fall, we fall back, 0600 becomes 0500, and that day will have 25 hours in it. As navigators, we're not too concerned about why it happens, whether it's because we're an agrarian society or we want more daylight. We're more concerned about, as we make our voyages, whether or not our departure country and our arrival country use daylight savings and what that means for when we need to show up. We call it daylight savings time here in the US, but other countries will refer to it as something like summertime. Let's draw the time zone that we're currently in and see how daylight savings time affects us. Our longitude up here in Newport, Rhode Island, is approximately 071 degrees, 15 minutes west. We'll find our zone descriptor by dividing that by 15 degrees, because there's 15 degrees in each time zone. First thing we'll do is convert 15 minutes into degrees. There's 60 minutes per degree, so we'll do 15 divided by 60, and that equals 0.25 degrees. So we'll rewrite our longitude as 071.25 degrees. We'll do our math, and we get 4.75. We know that all our zone descriptions have to be whole numbers, so in this case, we're going to round to the nearest whole number. In this case, it's 5. And then for the sign, we look at, since we're in the Western Hemisphere, it'll be plus. So our zone descriptor up here in Newport is ZD plus 5. Now let's draw that out to see what it looks like. So we know that we're in ZD plus 5. The next step is to find our central meridian, the middle meridian of our time zone. Each central meridian is divisible by 15, so in order to find ours, we'll take our zone descriptor plus 5 and multiply it by 15, and we get 75. So our central meridian is 075 degrees west, since we're plus. And if this over here is ZD plus Zulu, which is Greenwich, then in the spring, we have all the zone descriptors in between there. What we actually do is we go from ZD plus 5, and when we spring forward, we actually start using ZD plus 4. And then in the fall, what happens is we go from ZD plus 4, we fall back to the time zone of ZD plus 5. It's the same concept as advancing and retarding our clocks, but this will make more sense once we start talking about time zones. Next up, we have the international dateline, the IDL. That's 180 degrees of longitude. If the prime meridian is 000 degrees, on the other side of the world is the international dateline. And this is where the day actually starts. This is tricky because as we're transiting any other part of the world, whenever we enter a new time zone, we either advance our clocks an hour or retard them 1 hour. When you cross the international dateline, it's different. You either add a day or you subtract a day. And we'll look at that in the next lesson when we talk about time zones.